All right, so this is a homework problem from our textbook, and it's like application 7. Incentives for quitting smoking are group or individual. In a smoking cessation program, over 2,000 smokers who were trying to quit were randomly assigned to either the group program to help them quit or the individual program to help them quit. After 6 months in the program, 148 out of the 1,080 in the group program were successfully abstaining from smoking. Cool, they quit after the program. Hopefully they stayed quit. While 120 out of 990 in the individual program were successful. I put a little asterisk there because I have the source if anybody wants it. I'll add that to the spreadsheet in a sec. We wish to test to see if the data provide evidence of a difference in proportion. Okay, so remember we looked at difference in means the other day? Now we're going to see, okay, is the proportion of people who quit in the group program different than the proportion of people who quit in the individual program? Okay. And again, they're not the same number, so of course they're different, but is it a big deal that they're different? Are they far enough apart to say, whoa, the group program seems to work better than the individual, or the individual seems to work better, right? Now, how many of you like doing group work in classes? No one's raising their hand. I didn't until I realized if I could find the other right person in class that was smarter than me, like, yeah, I'm working with them. But sometimes it was just awkward and painful, right? So as I'm looking at this, I'm like, oh, if I was smoking and I wanted to quit, would I want to do it alone or would I want to be with other people? Some people are going to say, I need to be in a group. Others are going to say they want to do it alone, right? So I don't know which is better. So what are they saying here? The difference, we wish to see if this data provide evidence of a difference. Okay, is there a difference or not, right? They're not saying one's bigger than the other. Okay, so we're going to try and come up with a null and alternative hypothesis here with some correct notation, state what they mean in words, and then we're going to do a randomization distribution on this, and we're going to check it with a normal distribution calculation to see how they line up. We'll do it on the spreadsheet and in StatKey. All right, time to write stuff down. So let's see, there's my whiteboard. Let's take notes. All right, so what do we got? We have a quit smoking program. That's easier than writing smoking cessation for me. So quit smoking. And then there were two programs. One, there was the group program. They mentioned that first, so the group program. And two, they mentioned the individual program. Individual program. And each of those ended up having a proportion, right? The proportion of people who were able to quit in the group and the portion of people who were able to quit as individuals. So for parameters, we have two parameters at the moment. They are proportions, so we call them P's, not mu's. So I'm going to say P1, proportion 1. So in StatKey, they often put a 1 by the P or a 2, group 1, group 2. Sometimes I like to put a letter. So I'm going to do a PG for the group. That's going to be the same as P1. And then P2 will be my P individual. And what do these mean? This would be the proportion of people who quit smoking from the group program. And every time I do one of these in class and in my videos, I write down in words what my symbols mean. I highly suggest you do that because you can't write a conclusion unless you know this stuff up front. All right, PI or P2, that's going to be the proportion of people who quit smoking from the individual program. Now, these are the population parameters. I do not know them, right? I know the sample ones, those are p hats. So here I'm getting set up for my hypotheses. And So basically the question, the test they said was, is there a difference or not, right? So are they equal or not? So one way of stating the null hypothesis would be to state, oops, colon, does P1 equal P2? Now, alternatively, not the alternative hypothesis, but another way to write that is, are they different? Well, difference means subtract, right? So if I subtract the P2 to the left there, I could also state this as P1 minus P2 is 0. They're the same, there's no difference. The difference is 0. So that's another way to state the null hypothesis. The alternative hypothesis would be that they're not the same. They're far enough apart to say they're different. And the other way to write that would be to put the P2 to the left side and say P1 minus P2 is not equal to 0. I don't know if it's bigger or less. I don't know if the group's better than the individual. They're just not the same. Could have gone either way in the sample. So those are my hypotheses there. I don't think they mentioned a alpha here. Don't see one. All right, so I'm going to go for standard. Alpha is 0.05. So I did two things here, right? I read through the description of the study, and I wrote down what my parameters meant, and then based on those parameters, these are what I believe the hypotheses are. Okay. Now somebody might have came in and said, I'm sure the group is better. I'm sure the group is better. If that was true, then my alternative would have been P1 minus P2 would be greater than 0. If someone was insisting that should be the alternative. But here they just said difference or not. So that's what we're going to go with. That's the conservative thing to do. Next, we look at the data. Okay, sample data, what do we got? Sample data. All right, so we have a P1 hat. That would be also, we could call it PG for groups hat. Remember, we put a hat whenever we're referencing a sample. And I think that one was what, 148 out of 1080? Yep, 148 out of 1080 was that one. My P hat 2 from the sample, P individual hat, that was 120 out of 990. So that's the sample data. Now, it turns out to run the hypothesis test in StatKey, we need a couple of things. We need all three of these numbers, right? We need the count of the 148, we need that subsample size. We need the count of 120 plus that subsample size. The other thing we need to do, our sample statistic is going to be the difference in these two. And the way I chose to do the difference was I chose to take the group minus the individual, P1 minus P2. So I'm also going to make a note of that here too. So I want to know what is P1 hat minus P2 hat. So on my calculator, StatKey will calculate this for us. What is the 148 out of 1080 minus the 120 out of 990? Don't worry about getting that on a calculator. StatKey is going to give us decimals on these in a second. So what I want to do next, because I need to find the standard error and I need to find the p-value, I also want to find the z-score. All right, so next up, we want to know what's the standard error for this situation. Once we get the standard error, we can calculate a z-score. Once we have a z-score, we can double check the p-value. So we're going to do it in that order. And you need these four numbers in StatKey to pull this off. So we just got to go over to StatKey and figure out what page to be on. Let's do it. And again, if you have a question, please speak up. All right, so I'm going to just reuse one of these screens. All right, let's see. We are doing a hypothesis test. The question is it a single mean, a single proportion, a difference in means, or a difference in proportions? And this is a difference in proportions. Yeah, so always want to make sure we get the right one. So we go to the difference in proportions, and then we're going to throw our data in here, edit. And so I'm just going to type the numbers I got. 148 was the count for group 1. And the sample size for group 1 was 1080. Feel free to try this too, or just watch. 120 was my count for group 2, and the sample size for group 2 was 990. And I'm going to click OK and see what happens. Move this out of the way. All right, so StatKey says that to 3 decimal places, the first proportion's about 0.138, 0.137, 13.7%. The second group was about 12.1%. Okay, is 13, almost 14 higher than 12? Yeah. Is it a lot higher? I don't know. There's what, 2,000 people-ish in this study? And they say the difference in the two is 1.6% down here. All right, so I'm going to put those in my notes. 137, 121, and 16. All right, so this one right here was approximately 0.137, which is about 13.7 of those people percent quit. This one was about 12.1%. And the difference was about 0.016, which would be about 1.6% different. All right. Getting closer. We need a standard error next to evaluate how different these are. Yes, 13.7 is more, but is it a lot more when we're talking about 2,000-ish people? I don't know. And again, I haven't done this yet, so I don't know what's going to happen here. Let's see. Do we have the right null hypothesis here? P1 equals P2. Yep, that's the standard for differences. StatKey just gives it to us, so we're ready to generate thousands of samples. Off we go. I go for 7,000. Okay, there's 7,000. Am I doing a left tail, right tail, or two tail? Yeah, because I went for the not equal, it's a two tail test. It's usually a good idea to remind yourself because sometimes the data distracts me. So this is a two tail test. And when I think about the data in StatKey, I can see I have a positive difference. That's just on the right side. I might accidentally do a right tail test when I should have done a two tail. All right, so I definitely want to click two tail here because that's what the hypothesis said. All right, oops, I just turn it off. All right, remember, it's got to think about it for a minute. It's got to count up all those thousands of things. And then our sample difference is the 0.016. That's positive, so I got to make sure I put it in the right at the bottom. 0.016. StatKey says, drum roll, the p-value is the combination of these two numbers on the left and right at the top. So about 13 plus 13 is about 26-ish %. That's a pretty big p-value. Are these percentages much different then? Answer is no. The group program wasn't much different than the individual. It was higher, but it's not much higher, is what this is telling us. And again, I'll summarize why in a second. So again, the procedure is we get our data in the StatKey. We had to get the count and sample size for each of those two groups in there. Once we had that, StatKey gave us the null hypothesis. We didn't have to mess with it, and we generated thousands of samples. Once we do that, we then take our sample statistic and we decide where to plug that in on the bottom. Since it's bigger than 0, it's got to go on the right. So I just plugged it in down there. And I had to do it for a two-tail test. So StatKey is saying my p-value is 0.129 plus 0.129. So let's put that in our notes. Over here. Okay, so I'll come back to this standard error in the z-score in a second. The p-value is about that 0.129 plus 0.129. I'm just gonna do my mind as a calculator here. 9 and 9 is 8. Gives me a 5, 2. All right, so my p-value here is the 0.258, the combination of the two of those. What's my significance level, alpha? Well, we went with the standard. Alpha is 5%, 0.05. My p-value is greater than alpha. It's big, it's not low. So what's my decision? We get a big p-value. That's the probability of finding another sample like this when we expected there to be no difference. There's a 26% chance that we'll find another sample that's around this close. That can happen. right? It's like flipping a coin twice and getting heads twice in a row. Happens every day. So this is common. What this tells me is the data supports the null hypothesis that there's no difference. I'm failing to reject the null hypothesis here because I have a big p-value. Fail to reject the null. We're going to confirm this by getting the standard error, a z-score, and then using the normal distribution calculator, see if we get a similar p-value. So let's reflect back before we write a conclusion. Let's see, standard error is 0.015, okay. 0.015. So now I can calculate the z-score. The z-score is always whatever the sample statistic is minus whatever the null says divided by the standard error. All right, my sample is the 0.016. That's the difference in proportions. So switch to a different color here. This is going to start to blend in. So I have 0.016. My null hypothesis, from the second version, the value is 0 from the null. So I'm going to have 0.016 minus 0. I could skip that, but I'm going to write it to be clear. Divided by stat key claims the standard error for a situation like this is 0.015. Whip that out on a calculator. What are we going to get? I'm going to use my Desmos calculator for that. Fraction 0.016 minus 0 divided by 0.015. And stat key says the z-score is about 1.07-ish if we went to 2 decimal places. So my z-score is about 1.07 to 2 decimal places. All right, so I'm gonna make a quick sketch of that, and then I'm gonna go to the normal distribution calculator and see what's going on. So here's what my sketch is gonna look like. So horizontal axis, draw your best bell-shaped curve. That's my best one today. Right down the middle goes the value from the null hypothesis, which was there's no difference. The difference is 0. Now, think about z-scores for a minute. The 95% rule says that within 2 standard deviations, you get 95% of the data. We just found a z-score that's pretty darn close to 1, right? Z was 1.07-ish. That's about right here. This is a two-tailed test. So that means I have to reflect that z-score over to the other side to be about -1. And I got to figure out what's in these 2 red tails here. So that would be about -1.07, because you have to flip the z-score on a two-tail test. So we're going to go ask the standard deviation, sorry, the standard normal calculator and stat key what it thinks. And we should get around 25, 26% from that too. Let's make sure. So I'm going to leave this one here. I'm going to bring up a new stat key screen for comparison. Stat key. And this time I want to do the theoretical normal. And since I have a z-score, I don't have to mess with the 0 and the 1. If you didn't do a z-score, you would have to mess with those. But I did the z-score, so I'm just going to go and hit two-tail. And then down here, I'm going to enter the z-score I just calculated, which was about 1.07. And the theoretical one says it's about 14% plus 14%, which is 28%. I found mine was like 25.6%. They're in the ballpark of each other, right? They're both big numbers around 25%-ish. Was my z-score really 1.07? No, it was 1.066666. But then even then, this number here is rounded and this number here has been rounded. So I got a lot of rounding error between this number here and this number here. Okay, so to get 25.6 in one case and 28.4 in the other case, I have a lot of rounding error going on. Are they both telling me the same thing? Yeah, they're both saying this happens 28% of the time. There's no difference in the programs. They're about the same. Fail to reject the null, There's no difference. Now, just another thing to note here, whether I use stat key, the center is 0 for a difference in proportions or a difference in means. Whether I use the randomization version or I use the theoretical version, 0 is still in the middle both times. Okay. Whenever we look at a difference in proportions or a difference in means, what's always in the middle, no matter how you look at it? 0. We assume there is no difference. Difference is 0. Okay, here's the challenge. Based on what we know about this program, how would you write your conclusion? We know the decision. The decision is to fail to reject the null hypothesis. So I want you to think for a minute, try to write down one. I'm going to wait a second, then write down mine.